So let's see what we got here.
What's called magnetism of matter.
Jackie, if you don't mind, when you send me that email about the magnetism lecture, if you could kind of give me a hack in the video where you roughly, if it's like an hour in or something, where I can...
It's like between one video and the next video, they don't...
Okay.
There's a gap. There's like stuff on the board that wasn't in the previous.
Okay, all right, I'll have to see whether that, you know, whether that's okay or not. Otherwise, well, I'll have to redo it. So we have Gauss's law for both magnetic and electric fields. And to wit, we have flux, magnetic flux B, ring and roll, B dot dA is equal to 0. And this simply means that the number of magnetic field lines that leave a Gaussian surface will go back into it again. And you will not have a surplus, no matter what shape you choose. And this boils down to no monopoles. Because you may recall that Gauss's law said that this is the enclosed charge, and the magnetic quote charge is always paired. Okay. Now we notice also that magnetic field lines look a lot like induced electric field lines, such as we saw in the solenoid. They're cyclical, and so one could make an argument: are magnetic field lines really true? Are they induced? Are they really a true phenomenon of nature? And I can show. We can look at that if we have time. And of course, we had the Gauss's law for electric fields, which was E dot dA is equal to Q over epsilon naught. And so these are principles we've already danced with a little bit. And Maxwell's equations, this is the first two of them. The other two, we have some work to do still to understand them better. We've acquainted ourselves with the third one, which is law of induction, but there's more to the law of induction that Maxwell worked out that I haven't demonstrated yet. But we'll take a step back here. Magnetism of Earth. The dynamo effect of the core, the iron nickel core of Earth, produces comparatively weak magnetic effects at the surface. However, such B field is planet-wide. So on certain bodies in our solar system, we get local fields. The sun is an example where we have the sunspots. You have a north and south. But the sun doesn't really have a star-wide B field. In the case of planets that don't rotate, such as Venus, which is, but probably struck or time around the sun, its revolution time is 224 days, and its rotation period is 243 days. So the magnetic field of Venus is really not important. You don't get the dynamic effect there. the moon doesn't have a magnetic field. You can have some local magnetism from the rocks or caused by some effects from the solar wind, but there is no magnetic field there. And of course, these things affect what goes on. It is the orientation of the magnetic field of Earth. So the symbol for Earth is a circle with a cross through it like that. So that's what that means. Is canted to the rotational axis. The geographic North Pole, North Magnetic Pole, wanders through the Canadian Arctic. The islands of the Canadian Arctic. So when you get up in the north, compasses are useless because the pole is so close, the deviations can be radical. Okay, and magnetically, this pole is the south pole. Thus, all compasses point south. Exclamation mark. So we just paint the other end of the band, and then you still know which way north is. Pardon me?
Question on
Sure.
What do you mean by the orientation is magnetism or rotational?
So the north magnetic pole, such as it is not underneath the north pole of the Earth. It's off in the northern Arctic somewhere. So the axis of the magnetic field of Earth is offset from the axis of the Earth. And it's mainly because of the core of Earth, especially the outer core being liquid. So it kind of, sort of like a plasticky stuff that does what it wants to do. And either that or the central core of the Earth has rotated within the plastic so that its poles are a little bit different. Who knows? The Earth got hit pretty good, we think, when the moon was formed. We think a Mars-sized object hit the Earth, was obliterated. The Earth was egregiously damaged. It was probably still molten at the time. And this created a ring around the Earth, which then coalesced into the moon. The moon froze first because it's smaller, about 4.5 billion years ago. The Earth was still pretty hot until about 3.5 billion years ago. So whatever water we have, oceans and so forth, had to come after that because it would have boiled off. So, yeah. And this field reverses itself about every million years. So the magnetic field of Earth reverses roughly every million years. And Earth has little to no field for about 1,000 years. During the flip. tell you how the magnetic field of Earth is a bow shock and it protects us and all that, and it's probably true. But whatever's true, clearly the Earth has had many reversals, and we're still here. So it couldn't be that bad. So effects on Earth-based life seem to be benign. Whatever. So we don't know for sure. There was an event in 1859 called the Carrington event, and in which the sun, of course, is producing a tremendous amount of energy, and the Earth's, 150 million kilometers away. We get the smallest smidgen. If you think about the energy that we receive, we get about 1,300 joules per square meter, roughly speaking, or watts, I guess you'd probably better use. But the throughput of the sun is something like 3.8 times 10 to the 26 watts. It's a staggering figure. And most of that, it goes somewhere else, thankfully. So the problem is, once in a while, the sun, in its tumultuous behavior, will release a gob of plasma. Okay? Now, this is not just radiation, this is mass, and it's going this way or that. And this is known as a coronal mass ejection. And if that happens to hit us, it can, of course, create, because you got a lot more charged particles interacting with things. In 1859, we did not have a great deal of electrical supplies and equipment and so on. But for 4 days, the telegraphy system, at least in the United States, operated without batteries. So what that would do to our electrical systems and our equipment and so on, had we had such a storm, again, would be an open question. However, I think it was in the 30s or something, there was a solar effects that caused a blackout. And I know that into the 60s and so forth, there's been a tremendous amount of work done to make sure that the electrical systems are safe and don't fail for silly reasons. And obviously today with computers, we would be able to know this. The question is always going to be, how hardened is this? Will the computer that makes the decisions be damaged by the very thing it's trying to predict? Hopefully they're smart enough to know that. Okay, I would like to think so. So these are, and one of the advantages with the coronal mass ejections, they take about 2 or 3 days to get here. So it's not the 8-minute thing, with the flares. This takes time. So you can be ready for it, so to speak. Short-term ready, but still. So there's that possibility too. How do we know that they slip? We observe strips of opposite magnetic field polarization in the floor of the Atlantic Ocean. Now, I don't know here, this is not going to end well, but there's your Atlantic Ocean, and we have a mountain range that kind of goes down the middle like this, called the Mid-Atlantic Ridge. They're 14, 15,000 footers. And around the time of the Cretaceous impact 65 million years ago, the Atlantic Ocean was basically closed. And you had this Gondwana or Pangaea, whatever you want to call it, big megacontinent thing. And after the strike in this area here, it began to open. Now, I don't like coincidences, but on the other hand, we do have enough examples of rocks stuck in the wrong places that the Atlantic Ocean is open and closed at least 4 times. Because there's pieces of Europe stuck on Newfoundland and things like that, you know, and the smart people know how that is. However, when this opens, it's this seam in the tectonic plates that has this underwater volcanism that helps to spread it, okay? So the lava comes out of the crack, and in pretty, I mean, you get some hotspots like Iceland, for example, but, you know, in Iceland, so Iceland's fairly new, comparatively, because when the ocean opened and closed, there wasn't any in Iceland. That kind of happened because it was a hotspot. But anyhow, you've got this opening up, and this going on, and you get lava spreading across the ocean floor nearby, but it freezes because the water at the bottom of the ocean is about 4°C and it stays that way. So this freezes fairly quickly. Now these lava particles generally have a non-trivial iron content to them, and so as they begin and freeze, when their thermal energy stops being such a factor, and they're ferromagnetic anyway, they'll freeze in the orientation of the current magnetic field of Earth. And then that's it, it stays that way. And then if there's a flip later on, it goes the other way. So if we are exploring that, we can look at the polarity of these things and get a sense of the orientation and learn the periodicity of this and so on in a way that we wouldn't otherwise understand. So it's pretty neat, pretty amazing stuff. This 1,000-year thing does concern me, but I doubt if I'll be around to worry about it. Anyhow, as I write here, interesting reading. So if you have this interests you, there's lots to look at here. Magnetism and electrons. So, magnetic materials generally have this property due to the electrons within. As electrons produce an electron current in a wire, a magnetic field is formed. And we already know that. No one said, really? After writing the test on it? But however, we have 2 more ways electrons can cause a magnetic field involving quantum mechanics. Okay. And this will lead, of course, to we talked at the beginning of this, the bar magnet, the permanent magnet, that's like the magic one. There's nothing going on, there's no current, there's no whatever, and it works, right? An electron has spin, angular momentum, or simply spin, and we will use the capital S with a vector to describe this. And associated with spin is the spin magnetic dipole moment. Quantity mu sub s, where mu sub s is equal to minus E over m times the s vector. Now, I'm going to get to that in a second, but I just want to reiterate here, we have to be very careful what we think this means. The electron's diameter has yet to be measured. It is less than 10 to the minus 18. That's 1,000,000 times smaller than a proton. We don't know. So when you have a property called spin, it's easy to imply rotation, understandably. It was discovered as fine structure in spectra about 100 years ago. We have two lines very close together representing the two electrons in the same orbital. And until spectra had adequate resolution, you didn't see those. Okay, fine. So we name these things based on what we think is going on. Same as the angular momentum and so forth, where it's going around the nucleus. Well, perhaps, but if you look at the electrostatic forces involved and the size of this thing, it's going around the atom 10 to the 14 times a second. It's a staggering figure. Is it really doing that? I don't know. But those are, so we have to be cautious, and that's why I keep coming back to implying that there's a true danger, conceptual danger, in applying macroscopic ideas to quantum mechanical things. And it's easier for you to say we don't know than to try to create a model that is unjust. And that's one of the complaints I have with this instruction and introduce to kids is that we come up with these simple ideas so the kids will quote unquote get it. But getting it wrong is worse than not getting it as far as I'm concerned, because it's very hard to get rid of those ideas because they're easy, right? That's why they stick. Okay, so let's look, and since these numbers were of great interest a few minutes ago, we'll put them down and you have them in your notes. So the charge, so E is equal to the elementary charge, which is plus, just to be clear, 1.6 times 10 to the minus 19 coulombs. So the charge on an electron is negative E. Okay, we always have to remember that. And the mass of an electron is equal to 9.11 times 10 to the minus 31 kilograms. So S is different than mechanical rotational motion. So first off, S cannot be measured. Due to the uncertainty principle. However, we can measure a component along a chosen axis. And for this treatment, we'll use the Z axis. this component to is quantized. And can have only two values. So S sub Z then is equal to ms h over 2 pi, and ms is equal to plus or minus 1/2, or as often as called spin up or spin down. So up is the positive and down is the negative. You may hear that as well. So I think I wrote earlier, but I'll say it again, electrons are spin 1/2 particles. They're known as leptons. An electron in the current model is a fundamental particle. So I think when I first started, I talked about quarks, and I said, you know, you've got the up and the down quark, and the up quarks have plus 2/3, and the down quarks have minus 1/3. And it's easy to make an electron equal to 3 down quarks. And even though the arithmetic works, it's not true. Okay, it's not how they're made. So if you finish with me and you're confused about quantum mechanics, I've done my job. Sorry?
We don't even need you to do the job. I'm already confused.
Oh, good. Oh, so okay. Well, perhaps the confusion I induce or imbue will be at a greater level yet again. Get you to doubt even more of your learning. Create a real mess. So similarly, mu sub s sub z is equal to minus e over m sz. So, as you can expect from the definition here of S, if we only have a one axis, mu sub S is a prisoner to whatever's going on with S, right? It's not going to change, it's just a multiply. And mu sub S comma Z is equal to plus or minus EH over 4 pi m. So the 1/2 has been incorporated in here where it was not before. Quantity mu sub b equals pH over 4 pi m is equal to 9.27 times 10 to the minus 24 joules per Tesla. This is known as the Bohr magneton. Sorry, where am I looking? This is an S here.
No, under similarity.
Okay, so this is S comma Z. So this is the this is the dipole moment of S all on the Z axis. For the electron, mu sub s comma z is equal to 1 times mu sub b. Parenthesis, in more advanced studies, known as quantum electrodynamics, or QED as physicists love to call it. The 1 becomes slightly more. And yields I think it's 12 or so digits of precision. Now this is a bit dated, but it's okay. One of the ironies, of course, in a subject with lots of them, is that quantum mechanics, with all its probabilities and inexactitude, also generates one of the most precise numbers we can measure. So you can look it up if you want a bit further. The study of the nucleus and its behavior is called quantum chromodynamics. And one of the advantages of it, this is a bit older, a bit newer, pardon me, than the electron, and so the properties they chose for it are whimsical. And that's a good thing, because then we're not thinking about trying to envision some kind of physical phenomenon when we really can't. So you'll hear that the properties of the quarks and the other things in the nucleus would be strangeness, charm, whimsical quantities like that. So you just keep track of things, but it doesn't mean anything. Earlier, though, with the electron, especially because it's somehow orbiting the nucleus somehow, we decided to give it more basic physical properties without really knowing what it is. And that's understandable, but tragic perhaps as well. So if we take a particle like an electron here, so if our spin vector is oriented this way, our mu sub s is going to be going the other way because of the negative sign here. It's going to cause the vectors to be opposed to each other. And the local field then will look like this. So electrons do not, parenthesis we think, spin like tops. The intrinsic B field is explained by their properties. For electrons, mu sub s and s point in opposite directions. Making magnetic effects about 1,000 times greater than protons or neutrons. However, charge plays a part. The protons, we cannot get enough together. So they really don't count. Neutrons have very slight magnetic effects, but we can put a whole pile of them together because they do not repel. There's no electrostatic forces here. So, can assemble many, but neutrons have very slight magnetic effects. But the many is the important word here, because this can lead to things like neutron stars with biblical B fields. You know, we're very proud of the 2 or 3 Tesla B field we have in an MRI. You can, in the lab, you can have magnetic field strong enough to pull chairs across the floor. That's all very exciting. But the magnetic field in a neutron star could well be 20,000 times more, or even more. We have some stars that are so magnetic, they're called magnetons. The magnetic fields of these, you may have seen just in your passing, and I won't do formal notes on this, but just to give you a little perspective on it, you may have seen some, as a physical object, have jets, as they call them. So you have some object, and then there's a jet, like a pulsar does this. And you have a jet of energy or particles, whatever it is, streaming out of the poles typically. Well, this is collimated by the magnetic field, which is incredibly intense. And as you know, the field lines do not disturb particles traveling parallel. So the magnetic field line tends to focus the beam. And the narrower the beam and the straighter it is, tells us 2 things. Tells us, of course, it's energetic, which we can measure anyway. And secondly, it tells us how powerful the magnetic field is. So the narrowness, if you will, of the, and I love to call them jets, but you know, it's not really, you know, whatever you want to call it, but is a rough measure of magnetic field strength. Now we saw this even in a trivial way with our auroras. And the charges come in, okay, now we're not ejecting anything, but where that aurora oval occurs is a function of how strong the B field of Earth is. If the magnetic field of Earth is more our strength, it might even be closer, depending on where the atmosphere is, of course, too. All right. Orbital
moment. So we have mu orb is equal to negative E over 2m L orb, and L orb is the orbital angular momentum.
You know, of course, Bohr considered this in his atom, but we're dealing with quantum mechanics now. In a way, it's a little bit more obtuse than what Bohr did.
Again, L orb is quantized. Let us consider the angular momentum on the z-axis. So we have L orb comma z is equal to m sub L h over 2 pi, or h bar, where m sub L equals 0, comma, plus or minus 1, comma, plus or minus 2, 3 dots, and there's a limit based on the
Other aspects of the atom. So these are p orbitals, basically, right? So depends on the line where you are.
and u orb comma z equals minus m sub L EH over 4 pi m, and they're all finished. And also stated in terms of the Bohr magneton. You'll find that questions in this section a lot of times are not that calculation dense as much as they are testing your understanding of the words and the concepts, because you get a lot of new words here, and none of this makes any sense. Quantum mechanics. Yes, Sarah?
Is this can't read the subscript on M? Is that an,
It's a script L.
it's an L?
Yeah, it's the magnetic,
The orbital magnetic quantum number.
that's what this is here. So this is M sub L. And if I'm using a script L instead of a, because lowercase L's look like ones, right? So
In terms of the Bohr magneton, we have mu orb comma z equals minus m sub L mu b.
So it's going to be the quantum number times the Bohr magneton.
The potential energy
U is given
is equal to mu orb dot the external B field which then be equal to mu orb comma z times B external, because again we don't know the entire quantity because of
the uncertainty principles restrictions. This next little bit's kind of interesting.
what we call, I'm going to do it in the new section, sort of to try and combine what you think you know
From classical physics with this initial introduction into quantum mechanics here, and see if we have some reconciliation. So this is kind of useful. A loop model for electron orbits. So we're going to have this orbit, and the angular momentum will go up like so. Velocity is in this direction. This is an electron, so the current therefore goes the other way. It has a circular orbit mercifully, so we have a radius of r, and the entire thing has an area of A, which we would know to be pi r squared. So, using classical theory, let us see how close we come to the quantum mechanical QM. Mu r is equal to I times A. The current I is equal to Q over T. Thus, I is equal to EV divided by 2 pi r. So we have the charge and the time being at the bottom. Time is simply distance divided by velocity. So the reciprocal time is velocity divided by distance, right? So that's all makes sense. And Iris, if there's anything that you want to ask, you're certainly welcome. Just activate your mic and say question, because I'm busy here, I won't hear you, I won't see a text. Okay, so don't be afraid to do so. And area, of course, is equal to pi r squared, which I mentioned in the room. Remember that? So mu orb is equal to EV over 2 pi r squared, which is equal to, when we're all done, EVR over 2. To obtain an expression for L, we have L is equal to M times R cross V, right? Since R is orthogonal to V circle, then L is going to be equal to MRV for a magnitude. If you already know it goes up the top, we've already established the cross product here, so this is just a magnitude thing. U or is equal to minus E over 2M L or. So the definition at the top was minus E over 2M L or, right? Okay, so we get the same answer here. So using physics, we get the same answer. think it's cool that they did this in the textbook and give you a taste of how this sets up. Now we'll switch things a little bit here. Something you probably kind of know already, but we'll just say it anyway. Magnetic materials.
Question.
Yes, please.
Is the L on the top like a script L?
This is an E, this is the fundamental charge, pardon me? Oops.
Like L, or is that like a script L? Or is it
Yeah,
like
this, no, this is a, oh, okay, I see. So this is just general case, okay? So now we're going to do L orb. And we have the mass of the electron. And then we have R and V. So, now this, I've already combined it, I guess, in some respects, but let me just do this for fun here. So R is going to be 2 pi R, and we have V here. So I'm just trying to understand where we get the E from. This doesn't fit to me, but I was just looking back at it. Is it just the definition of it? Mu orb equals negative T over 2m?
No, I think it's because of the two, right? V or just the L over N, you said they took your name for the...
Okay. Just wondering, because we don't have an expression for the velocity of the thing, like how fast it's going around there. I'll have to think about it, and I just don't have it, and I don't want to delay it here, because it's not that important, but just interesting. That's not R either. That's wrong.
Isn't that current?
Pardon me?
Isn't that like the E?
Yeah, I guess you would, because you'd have a current there too. I have to, it seems like I need another line or two here, and it's just not in my head. We have mu orb equals IA.
It's on the right side, on the right panel.
Yeah,
It's all in.
it's all here, yeah. That's right. So this is the definition of mu orb, okay? So you've got this, okay, there you go. Thank you, Jackie, appreciate it. So let's just do it here. So then we would have mu orb is equal to IA, which is equal to EV over 2 pi R times pi R squared. If I did it right. And let's get the times, I shouldn't be writing that. So this goes, and that goes, and the square goes, and this goes. Then we get the EVR thing, which I already had. Because I had that here, right? Yeah, okay. So now,
You multiply by M over N.
right, okay. So then we do M over M here. That's going to give you exactly it, right? Okay, thank you. You can come on up and I'll sit there. No, I mean that in the best way, not of being mean or anything. It's just good for you to see that all, okay? So, all right, so let's put that through here. That gives us EMVR over 2M, which is simply mu sub S comma Z, which is equal to negative E over 2M L orb by substitution, because MVR is L orb, right? So, nicely done.
Where does the negative?
It's just because it's an electron, we know that. Okay, yeah. If I wasn't ending this, I'd have to improve my notes, but I can get away with it. So won't need them again, so it's, but good. All right, magnetic materials. So first we have diamagnetism. Diamagnetism and paramagnetism and ferromagnetism are the three different things. And we've already talked about induced electric fields by stretching molecules and so forth. Those things happen. Well, in many ways, we do the same thing with magnetism. And one of the things that MRIs do is you orient it and then let it go and see what it does. And when it relaxes, okay, that can tell you things about it. But, so that's incredibly simplistic, though. But so we have most common objects. Exhibit this form of magnetism. However, it is so feeble that it is often masked if the other two types of materials are available. Or let's say present. So in diamagnetism, weak magnetic dipoles are formed in such a material by an external B field. These effects vanish when the external field vanishes. Paramagnetism. So I didn't put anything here because it's pretty much everything, right? So, and that's why MRIs work on people, because first you're full of water. Some people like me are full of something else, but that's a different discussion. But you got 70% of water in you, depending on the day, and the rest of you. And so this diamagnetic property is one of the things that they take advantage of in the remarkable how you turn those signals into an image that's 3D. It's just awesome to me. It's pretty incredible. When I was first sick in '86 with Crohn's, we were still doing things the old-fashioned way. There were no MRIs. There was no CT scans. They were just getting one, and there was a big fight over it because it was $50 million or something. So everything was done with X-rays, just like it had been done for a long time. And so the availability today for the doctors to see what's wrong so they can act directly and not guess as much is pretty impressive, and really has helped and saved a lot of lives, because doctors aren't perfect and they try really hard and they really care, but they're humans. You know what it is when you get a diagnosis that isn't what you like. They always say to you, what? Get a second opinion. Deliberately. They mean that. They want a second opinion. They don't want to be wrong. But based on what they're seeing, that's what it's telling them. Our people have had appendicitis when appendix has ruptured badly and you've got an infection and so forth. It doesn't show very well. And they often say, we think it's appendicitis, but they pretty much have to go in and check. And now in the 70s, when I was your age, if someone had cancer or something like that, I don't know how many times I've heard they'd have exploratory surgery where they'd open them up and have a look, because they didn't know. They had blood tests that were weird or off the charts, and the x-rays were inconclusive and whatever, right? And I don't know how many times I've heard the story, because by the time a lot of these, especially in those days, a lot of the men, they were afraid of the doctor. They didn't like to get a needle or the indignities of medical treatment, so they put it off until they were so sick there wasn't anything anybody could do about it. And I'd say, I remember hearing people talk when I was like your age or younger. Well, they had Bill in the other day, and they opened him up and they just sewed him back up again, because when they got in there, they found inoperable cancers, which may have been operable anyway, but and so here's the poor guy who's already sick, and now he's got a big hole in him that has got to heal on top of that, and I know what that feels like. So it's pretty medieval. Anyhow, ferromagnetism, transition elements. Rare earths and actinides. So if we look at over here at our friendly periodic table, you've got, scandium to mercury. Let's ignore these other ones. And then the actinides, so actinium through, say, to uranium. Most of you don't have too much uranium in your basement, probably, thankfully, but those things exist. And that's the thing that surprises us, like I said before, when we're doing other work and suddenly you have these effects you didn't expect because of the properties of these materials. One of the aspects of engineering, it doesn't appeal to me particularly, but I certainly respect how important it is. It's just material science, is understanding what this stuff does so that we know what to make it out of and what not to make it out of. In a very simple sense, I remember they put a thing up about the size of a TTC bus. It was a little bigger now, I think. And it had all these patches on the side of it all over the place of different materials. And it's supposed to be exposed to space for a year. But of course, after that, Challenger didn't make it. So it ended up being there for 6 years. So the idea was to go up and pick it up and put it back in the shuttle's payload bay and bring it home. And the shuttle can't land with the same weight it takes off, but this thing was designed for that to work. And so anyhow, so one of the substances that was really got slaughtered up in orbit was Kevlar. Everyone's favorite material down here on Earth in so many ways did not withstand the radioactivity very well. So it's interesting how that turns out. So magnetic dipoles exist. In these materials. But are randomly aligned. The presence of an external B field aligns many of these. But if removed, the effect is soon lost due to thermal agitation. which leaves us with everyone's favorite type of magnetism. And this just goes back to, fundamental theory here. Why is it that, nickel and iron are so good at this and everything else isn't? That's the fun part, right? And being able to predict that, being able to predict the boiling point of a material, that'd be pretty exciting. So we have ferromagnetism. And this is, of course, how this stuff was found, because you had materials in nature that were naturally magnetic. And so they called it lodestone and things like that way back when. But the point is they became aware of it because it was this phenomenon of nature. And then you couple that with electromagnetism, which was found much later, I believe by Ørsted. And the story that I remember was that he was about to do an experiment, setting things up to do an experiment for his lecture, in the early 1820s or something. And he had compasses on his desk. And he energized the solenoids for just a test, I guess, to get them to work, and all the compasses changed direction. So that was a good afternoon. Ferromagnetism, of course, is iron and nickel and alloys. So, for example, steel is going to show this. And variations of steel, alloys of steel, like a stainless steel, for example, which is just a nickel steel, has very good properties that way too. So, some electrons in these materials are able to align dipoles creating by superposition a sensible B field. These effects persist after the external field is removed. If you want to make a permanent magnet, well, first off, a permanent magnet can be ruined by dropping it incessantly, and just the gyrations will cause lock of alignment. But the best way to get a magnet to stop working is to cook it, because when you heat it, the thermal agitation increases to the point where it fails. But in the case of ferromagnetic materials, you can take, if you want to make a permanent magnet, you get some molten steel or whatever molten, whatever it's going to be, and you put a pretty good B field in the environment, and you let the stuff cool while the magnetic field is on, and it'll freeze in that orientation, just like the Earth did, and that makes you a permanent magnet. So unless you heat it up again, or otherwise are treating it badly, these things will persist for quite a while. I remember we had these rare earth magnets. I think there was one here. Neodymium is everyone's favorite one right now too. And I remember about 15 years ago we had a student in AP Physics, and she would put in one of these neodymium magnets in her pocket, which was no bigger than a quarter, not very thick, looked like one of a watch battery or something like that. And then she'd go up to one of Mr. Lang's filing cabinets and put her rear end against it and open the drawer, because it was that strong. It would pull the drawer open. So she got quite a kick out of doing that. But I believe those magnets were ultimately the kind they were using for the physics project. So that's how they became aware of them. Okay. Now we're getting close to the good stuff here. Now we're not doing the magnetic field experiment this year quite the same as we did before, but to give you a sense of that experiment, which you can of course read on the lab manual, but we would
first take a, so this is just the magnetic experiment. Just to show you what we did, which leads into what I'm going to say. So we could take a solenoid, and we would probe inside it with the B field to see if the current that's going around it and the properties of the solenoid could be modeled, would model actually what you detect. And we had those bigger coils that are off to Amanda's left there in the cupboard, where you could actually get the probes inside. And the B field probes, the foot bends on them so you can get them in there, because they're Hall effect probes, so you can get them inside. And then we would also look at the magnetic field here as a function of R. And then we did the transformer exercise where you used AC. And because what happens is the transformer is a function, the frequency gets too high, the dipoles can't rotate fast enough, flip back and forth quick enough, and they just kind of move. And then what you'll find is your voltage will tail off to nothing. You have to use a powdered core if you're using really high frequency situations. So that was something to show people, just to make you aware of it. The other thing was, well, that's really what hysteresis is, but, and then the last thing I made people do as an option was that you would take, as you know, you've been doing everything by symmetry, which makes things comparatively easy. So now we take two solenoids at random angles with like poles facing. So you know that your magnetic field is going to be pretty crazy looking. You know, if you had opposite poles, then they just come together almost like straight lines. It's boring, right? So, and then what you would do, because the symmetry is all broken here, and you're dealing with edge effects and everything else, is you would use B sub R, and you'd have to write out some software, use your algebra engine, and actually integrate and produce the 3D field. Then you would measure the spots in between here and see if it mirrors up. That was the bonus to that lab, so that was kind of fun. So we used the Helmholtz coils because the smaller coils are kind of hard to work with. So we had these things. And if you put them reasonably close together, it sort of works. Did these originally for the fine beam tubes to cause auroras and particles, but the fine beam tubes failed after 30 years. And I condemned the power supply because there's 5,000 volts there, and if the insulation fails, we have a teacher in orbit, and so I didn't want to volunteer. Okay, so it just shows you some of the fun, and of course they'd have the best part of a month to do that, and you know, be here after school figuring it all out. So I couldn't run those because I thought it took too long to. I think the two we did do are, there's still things to do, and I think the circuit slide was important, but we at least get the data done in a fairly efficient way in comparison. So now, what day did I tell you the experiment, your papers due for quantum mechanics? Tuesday afternoon, great, okay, that's fine. So what we're going to do, my plan right now is to do graduation
What time of day is it?
for the, okay, well, we can discuss that. So what I'm going to do for the designations on your diplomas is I will not be able to include the second paper because obviously I can't mark it, you know, in 15 minutes if you want a decent job. Well, let's put it this way, a similar amount of effort. Let the decent part be up to you. But anyhow, so when I give you your diplomas on Tuesday the 17th at 1 o'clock in the gym, I sent the principal an email. He agrees in principle with this, pun intended. So just have to confirm that's all good, but I don't see why it wouldn't be. And then, so day 3 would be, apparently you're here, I think, or some of you are. We'll have to figure it out. But yeah, this will be at 1,300 hours, so everybody else will have left the building, so it shouldn't be too much contamination. We'll be in the gym, we'll spread out, and have that. And probably what I'll do is I'll announce the name, put the diploma on a table, then step back and let you come up and pick up your diploma. So it's a Byzantine way of doing it. There's no handshakes. I'd ask if someone has a half-decent camera, maybe we record what is going to probably be the last ceremony doing this.
Be kind of nice to have that too, so we'll see. So that's the way that's gonna happen, and we have the test on 3032 on Friday and Monday. So hopefully I'll get that done. Yeah, well, it's the only time I've been able to do that. I just don't have a choice. I'm out of time. And then graduation on Tuesday, and then credit recovery, which none of you need, right? And but you want sleep recovery. Okay.
This is the only class, so if I can recovery, then you would know about it.
Well, you'll have you can get ready for the 2 classes next semester. I have to get ready to teach a course I haven't seen in 20 years. So, but Mr. McMaster is very supportive. So, I suppose this will be an example of team teaching. So, and that's just fine with me because I don't care who gets credit. All I care is that what we get to you folks is what you need, because that course is important. And like I said, in first year you'll find the hardest math you take is algebra. Calculus makes sense. It's easy math. Okay, let's move on to some interesting things here. Maybe we'll actually get this done today. I stopped there, we're here. Induced B fields. So we have seen that a changing magnetic flux can produce an electric field. Okay, we call that induction. Okay, just to remind you of what I thought I covered the last couple of days. Changing magnetic flux, and we get an induced current, which of course means there's has to be an electric field there. So, and we have, so far, we're going to roll E dot ds is equal to negative dt sub v dt. And this is Faraday's law with Maxwell's addition to it, but Maxwell's not finished yet. In truth, yes, exclamation mark. Changing electric fields do, or electric fluxes, I guess we should say, yeah. Do beget magnetic fields. And we get B dot ds is equal to mu naught epsilon naught dV sub v dt. Now these constants are just scalings, so they're now I might just say, where did this come from? So, how so would be a reasonable question. We worked to show that this was so. All right, so let's consider a parallel plate capacitor. So once again, we have our 2 plates, and you have a current coming into the capacitor on one plate and a similar current leaving going the other way. And here's our plates seen from this direction. Now, let's think about what's happening here. The electric field is increasing, right? So As such, between the plates, as the charge on the plate goes up, the electric field goes up, so the flux, if the field, is going to be going up at least, or at minimum, changing. All right, so far so good. And what happens then is, because the flux is changing, we get, and once again we can use the right-hand rule here, fields into the page and growing. Yes. So into board and increasing. Use the right-hand rule. So thumb, okay, and we've got a magnetic field inside the capacitor, like so. So thumb, it's the electric field, fingers, magnetic field. So like I said, think about right-hand rule, 1, 2, 3, 4, whatever. I find just using the right-hand rule it makes common sense based on the geometry of what you're doing here. Okay, so the electric field's going into the board, inside this capacitor, so therefore the magnetic field is circulating. And the directions of these induced fields are opposite, so they can drive each other, which is really nice.
Mr. Manuel,
Yes.
what cross product are we considering when we use the right hand? Like, what's the cross product?
I'm not sure why we need a cross product. That's the right-hand system. There's the law of, like A cross B equals C, right? The right-hand rule was like, remember when I had the current and I had my thumb going direction of the current and this is the direction of the field? Okay, that's not a cross product. They're different beasts. One is a right-handed system, the other one is the right-hand rule. They're different ideas. All right? Yeah, and that's a good question because that can, so just remember right-handed system, right-hand rule. Right-hand system is definitely this. Okay, I agree. And from there. There wasn't as much, as you guys were really quiet today. A lot of times we'll see what tomorrow's like. But
The other class is louder.
Oh, is that what it is? Because of Ryan?
I
Okay.
listen to their,
Oh, on the thing here, yeah. Well, it's just like, I don't know how many times I sit here up at the front watching kids write these electromagnetism tests and you get all this kind of going on.
you barely put any questions.
Yeah,
It's
no,
like the first question.
Maybe, okay, well, you guys are like theoretical, here.
Well, like the questions that you did.
Well, I know the other groups did, so maybe they really didn't know what they were doing. Yes?
It was the first one.
What does the last part at minimum changing mean?
Or at minimum. So what I meant to say here is simply that the electric flux between the plates has to be changing. It can't be static. Okay? So it can be changing however way. You could be moving the plates apart. You could be doing all kinds of nonsense. That's the thing we have to remember here. Thank you for your question because it just perked another point here. One of the coolest seismometers is simply a capacitor where we change the plate, the vibration changes the spacing. Now that can be done, you can do lots of things, but what it's doing as well is producing a magnetic field. So as the plate changes, it changes the flux because the field's changing, because the stretching and so on, whereas the area stays the same. So you can get, and you get this, it's a very sensitive, very sensitive setup too when that happens currently. It would be on the moon, and this is in the 1960s. The seismometer was sensitive enough when it was positioned that it picked up the astronauts walking around, just their footfalls. So, and I remember that's in 16G too, so it's pretty amazing. Mr. Yao, a former student of mine, he actually went to the dollar store, bought 2 large serving plates and made a seismometer out of them, and just connected them to his fancy electronics that he had built. All right, that was rubbing this off, so let's do that. So these induced fields are in opposite directions. And thus will drive each other. Now, in mechanical physics, where we have resistance and hysteresis and so on, this dives out. But for a photon, for whatever a photon really is, you have an electric field and magnetic field, but there's no resistances, and so they drive each other, and that would, one model permeates it through space. We'll try to show you later on. So if we return then to Ampere's law, we have ring and roll BDS equals mu naught I enclosed. So mu naught I, or box around it, mu naught epsilon naught d phi sub e dt can produce a magnetic field. And so we have to improve this idea yet again. So the Ampere or Maxwell law we're going to have ring and roll B dot ds is equal to mu naught I enclosed plus mu naught epsilon naught d phi sub e dt. Now, of course, if you are in a circuit where there is none of this flux change, it's just zero, so you don't have to worry about it. You still have Ampere's law, just in addition to it, right? Displacement current. So we see that epsilon naught d phi sub e dt will have dimensions of current. Now you could try unit cancellation here. So this is the electric flux, so it's this E times A. So this is going to be, newtons meter squared per coulomb, and then you're going to have whatever the Byzantine units are of the permittivity. But if you cancel everything out, you should get an amp out of it, or a coulomb per second, or whatever, right? But you can do that for character purposes. So, although no, quote, real current flows through the capacitor, we call this displacement current. and this is generally I sub d. So you might also see something like this, where we have integral b dot ds is equal to mu naught I enclosed plus mu naught I sub d. Yes.
So is it like fair to say that you can think of the displacement current as like the induced current on the field?
I would suggest, yeah, it's really just this, okay? But it's going to be the same current that's flowing into the capacitor. If you just simply used your imagination that I sub d is just the current flowing through the capacitor, okay? Because if you're charging a capacitor without a resistor, then you don't have this, you have this, right? And then you can compute your magnetic field that way. All right, it's not really, you're not using an Amperian loop in the same way, right? So. Okay, so far we get here, we might have to do a little bit online tomorrow, but we might get this done, and we can get into some other stuff. Pardon me?
Oh, where are you?
Well, I'll put this up, I'll set this up tomorrow for you folks again. I think I've already done it. So that when they're done the test and finished, and I may not have to run around as much as I did this morning, we had a few fires to put out. Okay. So let us return to a charging capacitor. We have a real current. Charging the capacitor. How much we understand. As such, the electric field between the plates is increasing. And this yields the fictitious I sub d between the plates. The electric field due to, or causing I is we're going to say there, is found by the right-hand rule. I think that meant to be, because the magnetic field caused, I always look at it, doesn't make sense the other way. I sub d, quote, flows across the capacitor just electric currents and its induced magnetic field is also found by the right-hand rule. So we have Q is equal to epsilon naught EAE, or sorry, epsilon naught AE, okay? dQ dt is equal to I, this is equal to epsilon naught A dE dt. The area of the capacitor is not changing. And of course, the area times the changing field is just the flux, right? This is equal to epsilon naught dV sub ET, which is equal to ID. And so the current in the circuit is equal to the displacement current, as you might expect it to. Now let me see, what do we have here? We've got a quarter after. Yeah, okay, so not too bad. Now finding the induced magnetic field. Okay, so the direction is given by right-hand rule, and once again, just remember current's a positive charge movement, right? So just don't get fooled by that. I sub D or I can be used to determine the magnitude of the induced magnetic field. So if you think of the space between the plates as imaginary circuit of wire, the diameter of the plates, okay? We have to do a little bit of imagining here, but it's not that bad. So imagining space between the plates. Conductor with uniform current. I'll say current density, so it's distributed the same. Current's changing, of course, but I'll say current distribution, let's say it that way. The density probably changed too, so I don't want to get too precise. All right, now we learned that the magnetic field inside a conductor with current is equal to mu naught I sub D, in this case, divided by 2 pi r squared times r. This is the diameter, actually. So let's use r naught. So this would be the field inside, depending on where you wanted to choose it. Outside the capacitor, we have the out is equal to just the same equations, mu naught I sub D divided by 2 pi r, and the speed of the distance away. Now, I think I'm going to stop there.